Channel. This is session number 3 of our 6 virtual seminars that examines how to consistently optimize 5 key housing user experiences. Now, today's seminar is going to be focused on high performance homes, but we're not just going to talk about energy efficiency. The phrase high performance has to be more well-rounded, and we'll dig into ways that you can offer more to your customers. But before we get started, I wanted to make sure to call out the fact that this is Women in Construction Week. So congratulations to all of you women out there. My name is Mike Collignan, and I am the Housing 2.0 Program Manager. Now, if at any point you have questions, please don't hesitate to reach out to me via the chat box or by email. I'm going to put that email address into the chat box in just a little while. Have you met Sam Rashkin? He's formerly the Chief Architect at DOE's Building Technologies Office, but now is focused on creating and teaching the content for the Housing 2.0 program. That content is based largely on Sam's latest book, Housing 2.0, A Disruption Survival Guide. The full program is established to help empower you, our building professionals, to design and construct higher performance, healthier, more sustainable homes at a fraction of the cost. Sam's going to lead today's seminar, and he's also going to address your questions at the end. Now, before we get started, I wanted to tell you a little bit more about our sponsors. The first is Schneider Electric, who is driving the digital transformation of modern homes with smart and sustainable energy solutions for ultimate comfort and energy efficiency. Their connected home ecosystem of smart energy management solutions provides digital control of energy use throughout a home, from the grid via their smart electrical panel to their connected wiring devices. We're going to hear a little more about Schneider Electric today from JD Gill, so he's going to join us a little bit later. Next, we have Jinko Solar. They are a leading PV module manufacturer and energy storage system integrator. The company has deployed approximately 110 gigawatts of their Eagle modules in 160 countries globally, including more than 17 gigawatts right here in the United States. Eagle Storage brings together the best energy storage technology for turnkey hardware and energy storage services. We also have Mitsubishi Electric. Mitsubishi Electric promotes sustainable building through the electrification of residential and commercial heating and cooling products. Their mission is to advance technologies that increase energy efficiency and eliminate dependence on fossil fuels. And finally, we have Panasonic Healthy Indoor Living Solutions. They're helping builders across the country differentiate themselves with powerful, code-compliant, and cost-effective indoor air quality solutions that provide a safer environment for home buyers. Now, during the course of today's presentation, you can submit questions for Sam. Just use that questions box inside the GoToWebinar control panel. I'll review those questions and pose them to Sam after his presentation. All right, now it's time to hand it over to a guy who only deals with high performance, Mr. Sam Rashkin.
Hey, thank you so much, Mike, and welcome everyone. And today what we're going to do is talk about high performance homes. Efficiency is only a good start. Like Mike, I'm incredibly grateful to our great array of sponsors. They make this unique program possible, and we're really happy to bring this to the industry. So today's our 3rd webinar in our series this year, and we're going to talk about, again, high performance homes. The outline is, first, I'd like to give a context for Housing 2.0, why, what, and how. Then jump into our topic for today, high performance homes. We'll start with what we know with certainty, then go into the key building blocks that really comprise high performance. And then I want to talk about 5 imperatives that relate to one of the key building blocks, the enclosure. Then bring in JD to talk about innovation from Schneider Electric. Then we'll move on to how we do this faster, better, and cheaper. And very critical to that, as a complement, how we translate faster, better, cheaper. Like always, we always wrap up with open time for discussion at the end for any questions or discussion on this topic or anything related. So let's move in right now with why, what, and how for Housing 2.0. And the driving background data for this program that really speaks to what makes us excited about bringing this to you is this statistic that when you look at where we spend our time every day, from extensive research, surveying households, we find between the residence, work, dining, outdoors, vehicle, other indoor locations, we spend about 70% of our time almost in our homes. So home is where life happens. And post-COVID, I would assume we're probably getting closer to 75% of the time every day where we live. So home is truly the ultimate consumer product, which leads us to the why for Housing 2.0. Our core purpose, why we exist, are homes where life happens better. So that's the why. The what is basically a stool that's comprised of 5 experiences. And if I only have the home performance experience that we're going to talk about today, obviously this stool has no chance of standing. So the housing user experience optimization really entails a framework that has 5 key strategies: community design, performance, quality, and sales. And within those 5 strategies, we have 160 best practices. And the key about any framework is it's a way of having a process so you can consistently deliver the desired outcome. In this case, a better user experience for lower cost. How we do this is, again, a process that comes from this framework. And the best way to understand the process is compare it and contrast to the first cost business model that drives most of the industry. So the Housing 2.0 business model on the right, first cost on the left, and the first cost business model, we'll try to keep our costs as low as possible, investing in experts and special features. In contrast, the first part of the process with Housing 2.0 is optimize user experience by investing in experts and special features that may cost more, but if it's a sure thing in terms of a transformative user experience, it's an incredible investment. Then the key part is the next step, which is compared to the cost for material, labor, marketing, and sales. With Housing 2.0, we optimize value every step of the way. We're these special optimization lenses that get the most out of simple, lean, quality, integrated systems, and mass customization. All these are discussed at length in the Housing 2.0 program. And then that leads to lower cost savings with better value, experiences and owner cost savings. And the net is, from our calculations, about 30 to 70% of the cost of the home can be driven towards savings and added value. And so the last step is to translate that value with sales and service for better homes at lower cost. And this is the kind of the Housing 2.0 30,000 foot look. And I love empirical results that validate so much of what we teach. One example, Wash Construction, just by optimizing one of the experiences, the design, was able, after building the first building in a multifamily project, then build the second with 24% lower cost, just with design optimization. Again, we talk about these in the more detailed Housing 2.0 workshops. And the key thing is you have a resource that we recommend, the Housing 2.0 book, a disruption survival guide. Even my new grandson's in chapter 5, so we're excited he's humming along. The barcode on the right is a great way for you to kind of take a screen image and be able to get direct access to the book. So let's jump right in with today's topic, what we know with certainty about high performance homes. And I'm going to talk about 3 key things we know. 1, they've left the station. 2, they entail greater risks that have to be managed. 3, future readiness of these homes, and really ensuring they stand the test of time, is tied to also addressing hard trends. So let's look at each of these, starting with the high performance homes have left the station. And the first indication is just the HERS metrics, which are always compelling. The last full year data was 2023. Cumulatively, 3.6 million HERS ratings were completed, mostly predominantly in single family attached and detached homes. And the HERS ratings in 2023 were 338,000 homes roughly. This is a typo, 2022. And the average HERS index was about 58. So what we know basically is that already the industry is building way ahead of the average IECC HERS index home, about 70 to 80. So the industry is already moving way beyond code. But the next indicator is where the codes themselves are going. If we track the energy use index as a metric on the vertical axis, pegged to 1975 to 100, And look how far our codes have gone, particularly starting with the IECC codes in 2006. We see about a 40 to 60% increase in codes as we've gotten to 2012 through 2021 IECC. And I'll submit, by the time we get to 2015, 2018, and 2021 IECC, we're really looking at zero energy ready enclosures. And one of the reasons I know is this was a platform used at DOE for the Zero Energy Ready Home program. It was a 2015 IECC. It's a really strong code. The other way we know is just other codes happening around the country. There are about 7 states that are in process or already implementing zero energy codes. And we have another 10 states or so that are adopting the 2015 and higher IECC codes, which again are a platform for zero ready. The other way we know is just voluntary certifications. Already there are over 2.5 million Energy Star certified homes, which are well on their way getting to zero ready. And then the Zero Energy Ready Home program has grown, or all zero energy ready and zero energy home certifications have grown 440% in single family homes since 2020. This is an inventory of all the certifications in the US and Canada for zero energy and zero energy ready certifications done by the Environmental Building Alliance. And again, it's stunning just again how quickly and exponentially certifications, even in this space, zero and zero ready, are growing. And then we have the 45L tax credit. Now, this is finally a 10-year lock that the housing industry can finally bank on for substantial tax credits. And in the zero energy ready home space, that's $5,000 for single family homes, and also for multifamily with prevailing wage construction. For multifamily homes, it's $1,000 for zero ready, and Energy Star gets $2,500 and $500 respectively for single family and multifamily. And even manufactured houses get $2,500 for a Energy Star HUD code home that's certified to Energy Star. So these are locked in and are going to drive tremendous increases in all these programs. And then, of course, we're looking at mainstream builders and the directions that they're signaling, particularly the leaders in the industry. See here that Bees is announcing they're going to go to 100% all zero energy ready home certification for all the single family homes by 2025. And there's several other large national builders that are following this lead. In addition, in the HUD code space, Clayton is committed to building all their manufactured homes to DOE Zero Energy Ready Home by the end of last year, and they're well on the way to moving in that direction. So when you see even the lowest cost segment of the market-based housing portion of the industry going 100% zero ready, a very big signal where the industry is going. And if nothing else, I'm a big user experience believer that will always drive where products will go. And when you look at the superior user experience in advanced products that are moving towards sustainability, it's pretty impressive in terms of what's happening with electric vehicles. The companies, the design are important, but also the amazing performance improvements, ultra low fuel bills, ultra comfortable, ultra convenient, ultra low maintenance, ultra safe, superior acceleration and handling. These are experiences people want when they drive a car. Particularly not having to fuel a car at a gas station is a huge benefit. Overnight, just letting our cars charge at zero burden and kind of inconvenience. So it's amazing what happens in the car space. We believe the same thing has to happen because of the superior user experience in the home space as we move to zero electric homes. We'll have great communities and great design that we advocate with Housing 2.0, but also great performance in these homes that will blow away what we've been building up to this date. Ultra low energy bills, ultra comfortable, ultra convenient, smart, ultra low maintenance, ultra safe, and superior health protection and resilience. We believe this package of experiences will drive the market. So that's why we believe high performance has left the station. But in the process, we have to understand the greater risks that come along for the ride and manage them. So we go from a low performance enclosure to a high performance enclosure. We have more insulation, and more air sealing. So what that means is in a low performance enclosure, you have more thermal and airflow compared to a much reduced thermal and airflow in a high performance enclosure. And that makes a difference also in terms of what happens inside the assembly. Because now that less thermal flow is getting to the cold side of the assembly and less airflow is getting through to the cold side of the assembly, we have colder surfaces on the inside face of the cold side surface. So we have greater risks that all this kind of drives. The first is the moisture risk. We have more wetting potential because we have a colder surface, and less driving potential because we have less thermal flow getting to that cold surface. So we just have to be bulletproof at keeping moisture out and stopping airflow that can carry moisture vapor. Then on the comfort side, when you have ultra low loads, everything changes. You have dramatically reduced airflow going through the duct systems in an industry that has not spent a lot of attention and rigor building good airflow systems, duct systems. Second, we have much shorter cycles with ultra low loads, so the coils don't get cold as long and don't provide as much dehumidification capability. And we relied on the accidental dehumidification byproduct of air conditioning to provide the bulk, if not all, of the dehumidification needed for latent loads. So the shorter cycles create a whole different situation. And lastly, we have much longer swing seasons. So in the front end, we may start cooling much later in the year, and it may stop much earlier in the year. So we may have a month or two on the front and back end where we have no air conditioning, again with the accidental dehumidification, able to address the latent loads. So we really have to manage comfort in high performance enclosures. And lastly, with less dilution of contaminants happening with less air leakage, we have to manage and protect health inside these homes at a higher level. So all these things have to be managed. And the last part I want to talk about is future readiness and the hard trends that really will tell us what has to be done if we're going to build high performance homes that we expect to stand the test of time. What do we do? And we know without any doubt that the data in terms of greater frequency and magnitude of disasters is growing exponentially, so we have to manage more disaster risk. We know that water shortages are happening and becoming far more serious at just, again, a much more exponential rate. So we have to address water shortages in regions that are prone to drought. And we have to also address the fact that we're moving to electrification, and we must have solutions so that homes can adapt and either, if they're not constructed all electric, be able to go that direction with minimum cost burden and disruption. So these are the ways that we can be future ready. We know where the future is going. So this informs us about the key building blocks that really define high performance. And the why for performance, again, is high performance homes live better. It's just a superior user experience. So what do we and how do we get there? First, step one is we optimized efficient and smart. One of the reasons we're so glad that Schneider Electric's here today is really speak about their amazing innovation in the space of really integrating smart capabilities in homes at an incredibly heightened level. But we have to optimize efficient and smart across the entire set of components. One is enclosure, the other is equipment, and the other is all the components in terms of appliances and lighting that are in the home. So all the various features of the home have to be efficient and smart. Second, we have to manage risks. And three that we just talked about were moisture, comfort, and indoor air quality. And so these aren't extra credit. You have to be absolutely diligent managing. They're not hard to do, but you can no longer ignore them. And finally, the third and last step is to be future ready. Again, in lockstep with the hard trends, you want to be disaster ready, water efficient in regions that are prone to water shortages, and we want to be electric ready if we're not all electric right now. So this is very simply just following the risk factors, where the industry is going, and just being efficient and smart. Now, this leads me to coming up with a definition for high performance homes. I can't find any that work for me. So the one I've come up with is residence constructed with smart enclosure assemblies, systems, and components that ensure efficiency, durability, comfort, health, resilience, water conservation, and electric readiness. Far more all-encompassing than any definition that's probably out there right now, but I believe is critical if you're going to address all the key building blocks. And a sentence that usually follows the definition that I've come up with, it's great to have a beautiful home, but it's just as critical to have a high performance home that lives, lasts, and works better. So I'll submit this definition to the industry as one we should be using. So when we go to Housing 2.0, we're in the performance workshops and we look at what is the entire framework for how we optimize performance. We always use the same basic layout of why, what is the core purpose, why this experience is so essential, how do we optimize it, and what strategies get us there. So normally in a Housing 2.0 workshop, the why for performance is that protection matters. Protection from high bills, protection from comfort issues, protection from not maximizing convenience, protection from health issues, from water issues, from maintenance and durability, protection from safety issues, and protection from not having a home that will stand the test of time and be sustainable. And this is all that we try to address with a high performance home. The way we do it first is we optimize enclosure, and we do that with comprehensive building science. Then we optimize operation, and here we do it with efficient and smart. Again, efficient no longer stands alone. It's no longer extra credit to also be smart. It's efficient and smart. The smart train has left the station as well. Then optimize health. We do that with comprehensive indoor air quality. Optimize water with water efficient strategies, again, in regions particularly that are prone to shortages. Then we optimize resilience with disaster ready, and we optimize zero by choosing many of the options that are out in the market today for certifications to get on the path to zero. So today we're going to focus just on the enclosure and the building science that drives optimized enclosures, just to give you a hint of what we cover with the larger Housing 2.0 framework. So high performance homes, there are 5 enclosure imperatives that just have to be addressed, and we're going to talk about these. So the 5 imperatives are: 1, you have to optimize moisture flow control. Again, you have so much less drying potential, so much greater wetting potential. We have to keep bulk moisture and vapor flow under control. Second, airflow control is essential in any high performance enclosure. Third is thermal flow control with a comprehensive strategy for all the key factors that affect thermal flow. Then disaster resistance, and a key new imperative that we have to start addressing is productivity. I look at so much of the complication and detailed ways we build homes today that don't meet the affordability imperative. In terms of the larger industry challenges, we have to be more productive with how we build high performance enclosures. So let's talk about these one at a time. Moisture flow control involves, again, bulk moisture and vapor flow. And in terms of bulk moisture, we know the basic drivers. It's precipitation or snow, form of precipitation, wind-driven rain, gravity and bulk water that falls off the roof, accumulated water that gets on the ground, and then the water table below the ground. All these sources of bulk moisture have to be managed. And vapor flow, mostly it's diffusion and air leakage are the 2 key elements to how you manage vapor flow. And so in bulk moisture control, the essential thing is you've got to be bulletproof. You need a complete system. The roofs, the walls, the openings, penetrations, foundation, and the site all need comprehensive details for water control layers, flashing, heavy membranes where they apply, capillary breaks, water or damp proofing, drain tile, fabric filters, and slope to use gravity to carry water away from the site. And also I should mention from the roof. I do get concerned as I see more and more flat roofs being introduced into the architectural design aesthetic. And I know that the functional roof is to shed weather slopes or an asset. But anyway, this is a complete system. And the concept of flashing is pretty basic. And it's amazing how often we forget the details that make it work because we don't go back to the basics. So if I ask you as a test right now to flash this concept of a structure, hopefully you would know what to do, which you start at the bottom and you put your first water barrier layer flashing. And the key thing you can't forget, at the bottom, you need that little angle piece to create capillary break. If it's flat up against the surface and water can wick up, it's falling down behind the flashing and undermine its purpose. So this is the key thing. You start at the bottom and you do your first piece till it can attach to the next piece. Then you put the next in shingle fashion against that piece so it can attach to the next piece. Then you shingle up to the next piece. And on the back side of the piece, you have a piece that starts doing the same thing. And when you have a top, you have to have it capped again with the capillary breaks. And if you do all this, amazing things happen. Water sheds, and there's no water issues. And the amazing shortcuts I keep observing in the field will drive me crazy. We have no wiggle room. We have no grace period. We have to manage bulk moisture. We need comprehensive details. So when you look at details and ones that we do, and we see all the CAD drawings, they're all done with the same basic strategy: shingle fashion, and then the flashing to protect, and again, all the key details that manage water flow. That's what we do. And so we can look at something like the window flashing detail. And what we do in this case is we have house wrap, we cut it around the window, and we fold in the flaps against the jambs, and we have a flap at the top that we cut at an angle and lift up so we can insert a piece of drip cap flashing. So any water that falls off the weather barrier will flow over the window and down. So that's what we do on the front end. Okay, now when we go to the next step, what we're going to do is first put on the bottom pan flashing. Then on the jamb sides, we're going to have the jamb flashing tape over the bottom in shingle fashion. And lastly, right up against the drip cap flashing, we're going to put the top head tape go against that, and then we'll put down the flap from the house wrap over that whole assembly. And we have a completely shingled, fashioned water drainage assembly on the outside of the home. Now, the key detail that will sometimes be forgotten, when we attach the window, we will seal it to the frame, but we have to remember to leave the bottom free, so when all the water that may collect at the bottom has a path out. So again, all these details are applying the same principles over and over. Wherever you're flashing or doing weather barriers, we're always shingle fashion, making sure water has a path out, and then you just don't get into any issues. The key challenge we need to know with older homes, built maybe 2000, 2005 and earlier, is an incredibly high percentage of homes don't have pan flashing. So I would submit everything built before 2000, maybe 80, 90% of the homes don't have pan flashing. 100% of windows leak. So this kind of infrared image revealing the water leakage behind the window is a problem if we want to come back and start retrofitting this home with wall insulation, because we can't. We can't make that surface colder when it's getting wet, and therefore create conditions where now we can lead to moisture damage, mold issues that weren't happening maybe in the first place. We have to, with existing homes, almost pull the entire cladding system and add control layers, and that's a whole other topic, how we do that. But you see why new construction has a huge advantage, because it can do effective thermal control, because we can effectively manage the moisture if we do the bulk moisture control details the right way. And we'll talk about a few of these. We can't do stupid things that leave out a $5 or $6 piece of kick-out flashing at the bottom of where a roof intersects a wall, because the water running down the edge will just accumulate and create moisture risk. So we do that simple detail. We deflect the water away from the wall, and we manage the risk. Similarly, with the exposed edges of the roof sheathing, we want to have drip edge flashing at the edges, not kick out flashing. We want drip edge flashing at the edges so that, again, you have that last place for water to fall, drain away from the control layer, which is the roof underlayment. And notice how the drip edge flashing has those slight bends, again, to create a capillary break so we don't wick water up behind them. We're always doing the same details the same way. A big thing for capillary breaks on siding is putting and furring over the underlayment, not underlayment, the weather resistant barrier. So we have an air gap that creates positive drainage, and the water that gets behind 100% of claddings has a place to go. The one forgivable cladding material that you can get away without the air gap tends to be vinyl siding, which is the lowest cost siding. People have many issues with using plastics and petroleum-based products, and aesthetics maybe with that siding, but it does drain without the air gap. But almost any other cladding, you want to have the air gap. And notice on the right, you see a low-cost way of doing cladding, which is using foam strips. You only need about 1/4 inch to create enough depressurization for the water to drain down behind the cladding. And when vapor flow control comes in, we have to recognize the primary culprit is not diffusion, it's air leakage. It's the most critical strategy for how you manage vapor flow issues. So in terms of air leakage versus diffusion, if we take a 4x8 piece of drywall and then we put a 1-inch hole in it, the outcome in terms of entire moisture flow over a complete air conditioning season, spring to fall, it goes up from 3/4 quarts of water without a hole to 7 quarts with a hole, or 10 times greater vapor flow with a small amount of air leakage. Now in a cold climate, it gets even worse. It goes up from 1/3 quart of water over an entire heating season in winter to 30 quarts if there's a 1-inch hole, or 100 times greater vapor flow. And that's also probably where we have the greatest risk of condensation issues and moisture issues in cold climates. So you just see how militant and effective and just diligent we have to be about managing all these air leakage challenges and all the bulk moisture control details to really then be incredibly protected from these risk factors. Now, air leakage is also critical for energy loss. You can see this comparison of how much energy loss in cold climates is attributed to air leaks, windows and doors, ceiling and walls. You see air leakage right there is 3 times greater than either windows and doors, ceiling or walls, each 11%. So air leakage is a big deal when it comes to energy loss, which is why you see the numbers for ACH 50 air leakage targets across the country. And but they vary because in less cold climates, the impacts are less when the delta temperature difference is decreased from outdoors to indoors. So you would have this myriad of choices depending you want to do zero ready to passive house, Energy Star, and the IECC codes, what you would hit. I'm going to submit that we should just do 1.5 ACH 50 everywhere because one, it does minimize energy loss, but the reason why we should do this more rigorous approach everywhere is it also provides contaminant control. Now in hot, humid climates, it's just deadly to have higher leakage, allowing all that hot, humid outdoor air to migrate indoors. Also, when the outdoor air has smog or contaminants or dust or pollen or odors or just pests, you have all that enhanced control with more airtight buildings. I've lived in leaky buildings, I've lived in airtight buildings, and it's unbelievable the difference in amount of pests and odors and other factors with good airtightness. And then the greater disaster risk. You know, if there are wildfires, we don't have to worry about the incredibly dangerous outdoor smoky air infiltrating into the home. If it's incredibly windy storms, tornadoes, and hurricanes, we have less structural damage risk if we have more airtight construction. So it's more disaster resilient. And then lastly, it's so readily achievable. A lot of people think 3.0 ACH 50 is a hard target. It's just a matter of being, again, diligent about managing where the key air sealing details have to be managed. And so there are three best practices for how we manage airflow control: air barriers, air sealing, and then we aforementioned flashing that we do primarily for bulk moisture control anyway. And then we have these kinds of lists for air barriers. This is a basic kind of organization for the thermal bypass checklist that Energy Star Certified Home introduced. This is all these details. If we take a look at just one, drop ceilings, you'll see just why it's so important to have these kinds of air barriers. They can virtually undermine the performance of the thermal control layer. So here's a drop ceiling sketch where you see a condition I've seen so many times where the framing is done by the framing contractor. So they do everything all at once, all the framing, and they also build, let's say, a soffit for maybe a drop ceiling in the kitchen or a coffer detail. And because once the framing goes in, it's very hard to go back and put in a liner underneath the little attic section in that soffit or against the wall section. It's missing. So there's no air barrier underneath the attic insulation in the drop ceiling or against the wall. Let's say it's running a garage. So what happens is if it's really a cold day outside, like 20 degrees, it'll be 20 degrees in the attic and or the garage. And if it's 70 degrees indoors, the heat can go right through the drywall, which has very little resistance to heat flow. And you have fluffy insulation that's a good thermal barrier, but not an air barrier. You have a pressure gradient where you want to go from more to less, more heat to less heat. So you have effectively almost a convection going through the insulation air pockets because it doesn't have an air barrier. So this space will eventually migrate to some midpoint like 45 degrees. Now, when that happens, you basically have infrared images like this. This is a home in Phoenix in winter, probably on a 40-degree day, but the dark colors indicate cold temperatures, the light colors, warm temperatures and infrared images, and the complete thermal bypass that's happening in absence of the air barrier at all these extensive drop ceiling details creates tremendous amount of cold surfaces. In the summer, it would flip. You'd have hot surfaces from the hot attic migrating through. And so this is one condition that you worry about, but also the airflow that can get through to the cold surface in the case of, let's say, the wall can maybe, again, hit a cold surface and create some moisture problems as well. So it undermines the thermal control layer and it can create moisture problems. So air barriers are really important to put right along wherever the insulation is being installed. You want 6-sided assemblies where you have air barriers on each side of insulation that itself is not an air barrier. Closed cell spray foam would be an insulation that's both insulation and an air barrier. And these are what it might look like. On the left, you have a normal framed drop ceiling, and you can see it's adjoining a garage. So they put the OSB as the air barrier material up against both the garage vertical surface and the attic above. On the right, you see a drop ceiling where, again, it's adjoining a garage, and you have the drywall up against the attic above and the garage on the vertical surface. And key things, you have to air seal it airtight to complete the assembly. This is the air sealing checklist that we normally look at. It's penetrations, cracks, geometry. I'm not going to walk you through all these, but there's it's a matter of keeping track of all these features that create air leakage and then just sealing them appropriately, either with caulking, sealing, flashing where needed, where openings are too big. And take a look at, again, one detail like the drywall top plate, and again, see why these details are so important. So we have here a winter condition where the drywall at the wall is joining a ceiling facing the attic. And you see all the thermal bypass that's happening with the cold temperatures able to push through against the wall. And the reason that's happening is the drywall itself undulates as it's just nailed to the top plate with spacing with the nailing that allows airflow to go through. And again, the insulation in the attic that is fibrous will stop thermal flow, but it won't stop airflow. We have gradients more to less. We create convective forces that start to, again, be the thermal bypass to the insulation, and you have a cold surface. So what we can do is use seal sealer at the top plate installed so the drywall will gasket against it. Normal construction adhesive is not as good, but when you get to retrofits and you want to fix this details and avoid the problems, the only option you probably have is to spray foam the top to get something effective and fairly time efficient. So you kind of see what your options are. And when you have large opening like shafts, again, the first thing to do is flash the bigger opening, and then you seal where it goes against the key surfaces. What's interesting here is they did have the fire-rated caulk around the metal flue, as you would require, but back where the metal flashing goes against the sheathing adjoining the opening, they didn't seal or tape at the edges. So it's funny, again, you always find things where you just get it partially right. Another thing to know about airflow is the most egregious interface, and this is by far is the attic ceiling interface. And the reason the attic ceiling is the most critical almost everywhere in the country is you have first the greatest temperature difference between the attic and the house. The reason for that is mostly summer conditions. The summer attics can get up to 120, even in cold climates, up to 160 and 70 in the harder climates. And so you're looking at 50 to 70 degree differences between indoor air temperatures when they're about 70 degrees. In the winter, they'll be the same as outdoors. Basically, attic temperature will be the same as outdoors, but still, again, you have the full delta T in the winter. And then you have a constant pressure against the attic. The stack effect is the more buoyant hot air constantly pushing up like 15 CFM, 20 CFM up against the highest points of the house. And that's a constant pressure for air to look for and find any weak point and find the least resistance pathway to get out and relieve the pressure. So you have constant pressure up against the attic interface. And then again, you have this Swiss cheese of air barrier details, knee walls, dropped and raised ceilings and shafts and wind baffles. And then you have Swiss cheese of penetrations, duct boots, access panels, and aforementioned drywall to top plate, which all need air sealing. And then you have you have the most huge HVAC losses up in an attic and for air conditioning equipment. So it's just stunning that this is considered a acceptable location for heating and cooling systems. So this is the most egregious interface. It's important to know that. And then moving on to thermal flow, we have to recognize that it's not just enough to have a good amount of insulation quantity. It has to be installed well. You have to minimize thermal bridging. And then once you build a good framed enclosure or other enclosure, you have to recognize the windows are really detrimental to the whole wall R value if you don't use the right efficient window. And looking at each of these, it's important to recognize that there's greater accountability today with the much more widely available low-cost infrared cameras. Even I can attach a small $200 infrared camera to my smartphone and get some pretty good infrared images. Cameras used to cost $30,000, $40,000, and they'll reveal any weak point. Again, quantity, quality, thermal bridging, and windows. They'll reveal it right away. And so we have, again, a great platform for doing good thermal flow control with the latest energy codes. Here you see a comparison in this chart of 2015, 2018, and 2021 IECC requirements for slab, floor, basement or crawl space, ceiling, and frame walls. And what you see is the only difference with the 2021 IECC and 2015 and 2018 are the light blue gray shaded boxes. So the big thing I'll call your attention to is that for good reason, the 2021 IECC is finally providing some adult supervision and requiring some modicum of slab edge insulation in climate zones 3, 4, and 5. And it just either, in the case of 3, finally requiring slab edge insulation, in climate zones 4 and 5, bumping up the slab edge insulation to 4 feet from 2 feet depth. And you'll see that's just a critical, important addition. In the case of crawl spaces and basements, they're providing another option that's recommended, which is instead of just a blanket that would be R15 or a frame wall that's R19, they're recommending the frame wall 13 with a 5-inch like sheared polystyrene against the wall. So 2021 gives you this other prescriptive option that's recommended. In the ceiling or the attic, they're bumping climate zones 2 and 3 from 38 to 49, 49 to 60. Recognize that's not as difficult as you would think. When you have a raised hill truss, that right away reduces the prescriptive requirement about to R38 or so in climate zones 2 and 3, and it reduces it from 60 to almost to 49. And then if you do insulation on the slope, you even get further reductions in what you have to do for the attic insulation. So where it looks prescriptively pretty rigorous, it's less if you do what everyone should do, which is raised hill truss and attics. And lastly, on frame walls, it's just recommending greater amount of thermal bridging control with thicker amount of continuous insulation in climate zones 4 and higher. So that's the basic difference between between the 2021 IACC and the 2015 and 2018. And they're all really prudent recommendations or prudent additional enhancements that everyone should be doing. And the amazing thing that happens when you do a 2021 IACC is what you can say as a builder. Compared to our minimum code and even Energy Star competitors, our home won't be obsolete in the next 3 or 4 years. Wouldn't you agree the largest investment of a lifetime, homes should stand the test of time? And for that small little investment and the amazing risk factors it mitigates for you as a builder, you're able to just completely differentiate from the builders who aren't building to the latest code, and even the Energy Star builders who will be building to 2015 versus 2018 and 2021. So again, a recommendation, everyone to go to 2021. But even if you do those good quantity amounts of insulation, you'll be undermined if your installation quality doesn't match. Our value killers are gaps, voids, compression, and misalignment just will every time undermine the good intentions of a good amount of insulation. And you see what happens here on the left with this band joist configuration. We'll have an infrared image like this on the left. And so we have solutions like spray foam and band joist would be one to mitigate that risk factor. Now, when it comes to thermal flow control, I'm really working so hard to get the industry to embrace that we have to do better. If you look at all the basic options you have, conventional framing is about 25 to 30% framing factor. So huge amount of your wall is 1/4 the insulation. Advanced framing still almost 20% framing factor. Staggered studs would be 12%, double wall 10%. This is again because of all the framing at sill plates and top plates and around windows and doors. And then when you get to the advanced wall system, structural insulated panels are 5% framing factor, and continuous insulation will be 2%. I'm going to suggest that in 2024, these are not good enough. It's far too excessive thermal bridging. Plus, you have all these quality challenges installing insulation in these wall assemblies, and you still have very high moisture control risk because you have the absolute coldest surfaces as you go from left to right. Your surface inside the cavity keeps getting colder and colder, and your risk factors keep getting higher and higher. So these choices minimize your thermal bridging. Plus, you have ensured quality installed insulation, at least with SIPs and with the continuous insulation portion of the framing with continuous insulation. And some SIPs has no vapor flow going through the assembly. You have almost zero moisture control risk. Rigid insulation, you're minimized depending on using the proper thickness of continuous insulation. If you don't use the right amount of thickness, which many builders are prone to want to resist, because once you get thicker and thicker, you can no longer nail the rigid insulation, you have to screw it in, which is time consuming and expensive. And the reason that you have to screw in the insulation as it gets thicker is you're effectively cantilevering your cladding 1.5 inches or more when it gets that depth. And so the screws provide the extra structural support to manage that cantilevering effect of the cladding being really have a 1.5 inch airspace before it reaches the frame, the sheathing, and the studs. So, again, these are your options. We'll talk more about them later. I mentioned the adult supervision. We've got to get to the slab edge insulation. Here you see that you have a superhighway for heat to get out in the winter when it's colder outside, and for heat to get in when it's hot outside and air conditioned inside. And the infrared images show you just what a egregious thermal flow offender that the slab edge insulation is. So the 2021 IECC is your friend, and you can use more simple, low-cost details like rigid insulation flashed against the foundation, or they're more advanced systems where the rigid insulation is both your slab edge insulation and it's your form for pouring the concrete, and you have the entire concrete thermally broken from the ground. I mentioned last part is the windows can be a complete whole wall R value killer. Again, the infrared images show you that you can have a really well insulated wall, and you have like a funnel effect where thermal flow can just be pouring out the windows and undermine all the good intentions with a really good wall system, advanced framing, double walls, staggered studs, even SIPs. We have to just basically recognize the importance of windows in cold climates, particularly. And so I just ran some calculations just to show you what happens when you use an Energy Star window with a U value 0.3 compared to a R7 window, which is 0.15 U value, and use it with various wall insulated, cavity wall insulation assemblies. R18 is a 6-inch wall, R39 is roughly about a 13-inch wall, R60 is roughly a 20-inch wall. And you see what happens basically, we have the effective R value compared to the insulated wall R value in the boxes. So with an Energy Star window, that's 0.3 U value. My R18 frame wall drops in terms of the whole wall R value, including windows, to R11, a 40% drop. By the time we get to an R60 wall, that Energy Star window results in a 70% drop to only R17. With a 13-inch R39 wall, it drops 60%. And most importantly, I can keep the 6-inch wall instead of the 13-inch wall and get almost identical performance to the 13-inch wall by using a R7 window. Later, I'll talk about a new innovation where I can get an R7 window at only a small extra cost and get the same performance as that R39 wall with a 6-inch advanced framing wall. So windows are just a huge impact on the overall thermal performance, and we have to recognize the importance of windows. And the next imperative is disaster resistance. This is just the new reality. This is where we are. One is this incredibly greater risk because of the exponentially increasing frequency of storms, the exponentially increasing magnitude of storms, and the exponentially increased expense incurred because of these storms. And let's look at that one at a time and recognize first there's nowhere to hide. When we track US billion-dollar weather and climate disasters from 1980 to 2016, the maps show you virtually there's nowhere to go for droughts and heat waves. Winter storms are in the usual suspects, and some surprising suspects. Some major storms we saw in Texas the last few years that took out power and just slammed the entire state. Obviously, hurricanes and cyclones are basically in the Gulf region and the Atlantic seaboard. Flooding is in most of the country except the dry Southwest and mountain states. Wildfires in the whole western portion of the country, and severe local storms, the whole middle and eastern seaboard of the country. So virtually there's almost nowhere to go. And the estimated market value for 43% of the homes in the US counties with high risk is $6.6 trillion. So almost half the US counties in the country have high exposure to disaster risk. And the market value for these homes is $6.6 trillion. There's nothing close to that amount of money in reserves by the insurance industry that cannot manage this risk. And because of that, they're leaving the markets. They know they can't manage the risk. So, good luck trying to get wildfire insurance in California and storm insurance in Florida and an increasing number of states where companies are just pulling out. And they're leaving for all the obvious reasons: the growing exposure, the stark increase in construction costs for when they have to replace damage. They're replacing it, incredible increased costs, 55% from 2019 to 2022, just the last 3 years. And the reinsurance market just wants nothing to do with these risk exposures, are imposing 30 to 40% increases to the insurance industry. So they're just leaving in droves. Sometimes you're lucky to have one option in some states. And then as a result, the costs have gone up like crazy. North Carolina, just in the last year, the insurance industry submitted for over a 40% increase statewide. Florida has seen over 100% increase the last 3 years. It's happening all across the country. Insurance costs are just taking down so many homeowners' ability to afford living in the homes they currently locate in. And then we get to productivity, and we all know these issues that, we want to build high performance enclosures, but the quality of the trades, the skills they have, the availability is just insane. Over 90% of builders reported framing crew and carpenter shortages in 2022, trades most critical to enclosures. Of course, insulation contractors are also important, but that's when 90+% of the industry is fighting for trade. They start accepting almost any quality they can get. Something with a pulse will do, and then everything starts to suffer behind that. And it's not going away. The Home Builder Institute calculates we need 700,000 plus workers each year just to meet and combat the current 1.5 million home shortage that the housing industry is confronted. New article I read a couple of days ago, I think, puts total shortage of homes getting closer to 12, 14 million cumulative that needs to be built to meet the demand for new households. On top of that, the average construction worker age is over 42, and for every 5 workers who retire, there are only 2 in the pipeline coming in behind to replace them. This is a cliff. We're marching towards it. There are less workers. It's not enough that you're a high performance enclosure. The new imperative is, can you be built with a shrinking labor force that has less quality? That's your new reality. That's the question you have to ask. And the other thing about productivity, to tell you that we've got a problem, is just 2 images. This is a home being built in 1877 in Omaha, Nebraska, compared to one being built this year, 150 years, and just marvel, be stunned at the lack of innovation. Just look at the same framing strewn across the job site and the waste strewn across the job site, the same lack of ergonomics and safety factors, and how workers are constructing the homes. Nothing has changed of any substance. We've gone from Western platform from balloon framing to Western platform. We've gone from dimensional lumber to engineered lumber, some little improvements in connectors and power tools, but this is a stunning glacial amount of innovation. And we see it in the numbers. When McKinsey & Company calculates productivity over time, productivity is a value added per worker. That's basically how it's measured. Construction is unique. It's the only industry that has negative productivity growth in the last 3-4 decades. And manufacturing's had double what construction's had. And the cost of this, again, calculated in another study by McKinsey & Company, to the entire construction industry is $200 billion that could be closed with adopting 21st century manufacturing methods. The way we're constructing homes is not affordable today. We got to build enclosures in a way that the consumer can actually afford the product. And a lot of the cost comes from just cycle time, from the lack of productivity. And cycle time has huge impacts on the cost the builder incurs and the price they pass down to the buyer. Cost savings accrue from just reducing carrying costs, increasing efficiency of how you work, and mitigating interest that you don't have to pay when you finish the job in a reduced amount of time. Enhanced profitability goes to the bottom line because of cash flow improvements, better pricing, and far, far better sales and closing. If the velocity of sales and closing results in building an extra 2, 3, 4 homes a year, and I'm making 60, 70,000 net margin per house, that's hundreds of thousands of dollars per year if I can build a few extra homes a year in cost just attributed to the bottom line profitability because of not having productivity. And then the risk factors cost money. Because it takes longer, you're not as adaptable to market conditions, you're more exposed to inflation factors and economic uncertainties, whether it's design trend changes, whether it's the job market or the overall economy taking hits, will affect your ability to sell, market, and price your product. Time is a huge cost, and the fact that we build glacially today does not work anymore. And all those benefits are not included in the bidding process. Okay, now I'm going to pass along to JD some innovation from Schneider Electric. We couldn't be more excited to have in this module because, like we say, smart is the new imperative, and they have some amazing innovation to offer you. So I'm going to let JD talk about what Schneider Electric's doing.
All right. Thanks, Sam. Appreciate it. I'm going to share my screen. Sam, maybe if you can confirm once you got it.
Will do.
Okay.
You're good, JD.
Got it. All right, perfect. Good afternoon, everyone. Thanks, Sam, for having me. And yeah, kind of gonna go play off your title, but I'm tweaking it a little bit. So I'm talking about high performance homes, but energy efficiency is really only one piece of it. So let's dive into what we got to show here. So I think, Sam, you're covering a lot of this, and I know we've shown this slide many times, but just some macro events that are happening in the industry today. So sustainability, when it comes to sustainability, we're still seeing a large increase in residential solar, even from 22 to 23, about 30% increase year over year. Along with solar, we're seeing resilience being a big part of it as well. So homeowners are wanting to add batteries as a backup. So whether it's resilience for PSPSs, power safety public shutoffs, or if it's the weather-related events that Sam was just talking about that are happening more and more often, whether it's wildfires in California all the way to hurricanes on the East Coast. So we're looking at resiliency there, not only with batteries, but even with EVs. EVs becoming more and more popular. We are seeing EV to home or vehicle to home via bidirectional charging becoming more and more popular. So instead of having a couple of batteries on the side of the house, maybe folks are using EVs to power their house in outages or to increase their efficiency. Speaking of efficiency, utility rates are just skyrocketing over the last 10 years, roughly a 25% increase across the nation. California specifically, we're talking over 100% increase in utility rates in the last 10 years. So it's vital for homeowners to be more efficient with energy that they're using. That all being said, we still, the homeowner still wants personalization. They want to be comfortable, but they also want to have savings, right, from that. So what's that balance, and how do we achieve that? So talking about what consumers want, I'm going to talk about Maslow's hierarchy of needs. So a little bit of a philosophy lesson if you guys are not familiar with that. We are going to talk about this in the realm of what consumers want. So Maslow said, in terms of basic needs, safety and physiological needs are the foundation. If you don't have those, you can't add to the layers above it. So resiliency for homeowners is really the number one foundation. So that means having power from the grid at all times. Taking a look at the next evolution, energy efficiency is a part of it, right? Existing homeowners are looking at energy efficiency upgrades as a top item. Homes are going more electric when it comes to heat pump water heaters, electric stoves, etc. And looking at the smart home side of things, I mean, now a new home, I call it smart standard, but doorbells and thermostats, most homes aren't putting the standard ones in. They're always going to be a smart version of those, and we feel like the electrical panel is that next step. Finally, self-actualization is the top tier of this hierarchy of needs, and that attains to sustainability, right? Having net zero homes they're becoming more and more important to customers, and even for builders, there's tax credits involved, right? But if none of these top layers matter if there is a effect to the power or that resiliency piece, right? So if the homeowners don't have that safety, that security of the grid or any sort of power source, those top layers won't matter. So let's talk about those pieces in terms of what it can mean in a potential additions to the home in terms of product. So looking at resiliency, that could possibly mean adding a smart electrical panel to manage some of those loads, as well as adding a home battery storage, to have that backup resiliency in terms of outages, whether it's grid related or weather related. Next, we have energy efficiency in smart homes. So that really starts with power monitoring, right? Really visualizing your energy, seeing what items are the big power sources, and how you can change your habits to maybe work around time of use, utility, time of use rates, right? So visually seeing what you're using is step one. Step two there is then adding levels of control if needed, right? Whether it's at the panel level or at the device or room by room level via switches, dimmers, and receptacles. So lastly, right, top of the pyramid here is sustainability. Ideally, we want to automate, minimize our carbon footprint, but maximize savings from the utility, right? So that is taking all these parts and pieces, combining them into one space where the homeowner can, achieve all of this, but at the same time, they don't want to be the facility manager of their home. So it's really automating all these parts and pieces to maximize that efficiency for the homeowner, and ultimately, for the bottom dollar in their checkbook. So that was just a quick 5 minutes, but just some contact information here, and I think we'll have question and answers at the end. But Sam, thanks for the time.
Thank you, JD. And if people do have questions for JD, they certainly can send them into the chat box. And JD, I would ask if you would simply put your email address into the chat box for everyone as well, in case they think of some questions a little bit later on. Sam, I see you're back on.
Sure, will do.
Hey, great, Mike. Is my screen back on?
Not yet. We got your camera. Let's get I think Mary's working on switching the screen back over to you, and now it's back on.
Hey, fantastic. Hey, thanks, JD. And again, I encourage everyone to take a good, deep look at Schneider Electric. They package everything into a incredibly elegant, simple package versus all these different moving parts that have to be assembled. So we love their innovation in the smart space. Okay, moving on, let's talk about if we have all these details and best practices for how we get to high performance enclosures, how do we do it faster, better, cheaper? And that's going to be the topic here. I'm going to cover a few options and then do a deep dive into one. One example would be an obvious one that a lot of us have switched to would be the unvent to crawl space. It's just so far superior to a vent and crawl space because one, it's faster. You look at all the time it takes to insulate the floor of a home, and just and details you have to do anyway, just for sometimes radon protection and just keeping moisture from the ground by having a vapor retarder down against the soil. We can do reduce maybe cycle time a day. We have better thermal control. We have better moisture control, far better comfort than having a crawl space that's outdoor temperature and high humidity. We have that semi-conditioned space that can be used for storage and HVAC. And we just have a lot less risk, which is also just a better living experience. And we save money on energy. We save money on cycle time. We save money on far less insulation to insulate the crawl space perimeter wall versus the entire floor footprint. And we eliminate all the costs for all the venting. So this is, just an obvious innovation everyone should be using where they build markets with crawl spaces going vented. In the case of foundations, we have basements. I'm always amazed how slow the uptake is with precast concrete foundations. We compare a concrete foundation on the left with a precast. The concrete foundation, first of all, again, we recommend the extruded polystyrene against the wall as basically a complete thermal bridge and a buffer against condensation on the cold surface. And then we build a frame wall with insulation and then the drywall. If we only have that one drain tile around perimeter, we need to have a conduit through the slab every 6 feet on center to let water and moisture accumulating under the slab have a pathway to the drain tile. We have a lot of expenses. In contrast, with a precast concrete foundation, one, it goes in like in 1 day. So you're probably going to save a fair amount of time in construction. Plus, you can build it in winter and sometimes do construction that you can otherwise not do in cold weather. And then it's stronger because it's an effective bond beam. It has far greater moisture protection. It's built in indoor conditions with 5,000 PSI concrete compared to 3,000 PSI concrete poured in on site. So it's almost like moisture proof as it's constructed. You have a clear path to the drain tile because it's not on a footing blocking the path of moisture to the drain tile. And that's because it's not like a bond beam that just sits on gravel. It has much more dimensional accuracy. It's much more usable space because the thickness of the whole assembly might be 5 or 6 inches less thick for a conditioned space. It has the framing and the extruded poly. So you may get 80, 90 square feet. That alone might be worth $100 a square foot, might be $9,000 or $10,000 of value there. And it uses 70% less concrete because it's so much more material efficient, which is much better for carbon footprint and just less use of resource materials. And the cost savings of the cycle time and with the integrated furring, it means an insulation. You don't have to spend for all the insulation and framing that you normally do for a finished basement. So this is a very compelling innovation, and I'm just surprised more high performance homes don't use it. Then we have that triple glazed window in cold weather, compelling business case we talked about earlier. And what's exciting, we now have the thin triple lowy window. The 3 manufacturers that offer this window, and essentially what they use in the inner glass layer, the middle, instead of a normal glass, they use much more thin glass like you would use for LED TV. This allows the extrusion to be the same depth as a double glazed window, where a normal triple glazed window requires a manufacturer to reset the whole manufacturing process to allow for a thicker windows product. So it's faster because it's lightweight and easy to install, not nearly as heavy as the triple glazed window. We can get R5 to R10 instead of R3, so it's better. It has enhanced comfort, less condensation risk than a normal double glazed window. And the cost savings are a small cost premium because the manufacturer plant doesn't have to retool for that thicker extrusion for the window. The thin float glass used in TVs is widely available at much lower cost, and krypton gases drop in cost substantially, which also enhances the thermal performance. And their other cost savings will be when you use a thin triple, you'll probably be able to offset other energy efficiency measures that you no longer need to do as a net credit against the cost of the window. So again, this is a faster, better, cheaper option. Real excited to see a number of manufacturers come out with this product finally. And then I'm going to talk more in depth about SIP, structural insulated panels, because I spent a lot of time with this one. And again, I'm amazed that we are building such a complicated system with conventional framing versus assembling panels on site. In fact, the SIP optimizes all 5 imperatives: moisture flow control, airflow control, thermal flow control, productivity, and resilience. It basically goes through the entire list of must-haves, I believe, in a 2024 enclosure. And it starts just with its basic configuration. Now you have this optimized insulation, this foam core that has no gaps, voids, compressions. It's almost a perfect material, and it allows no vapor flow through it when you have a complete optimized exterior and interior skin. So this is like building a Yeti cooler for a for optimized thermal performance of your home. And so this is basically just in concept, just so far superior to a frame system and uses about half the wood. So again, another kind of environmental carbon footprint benefit to the whole technology. This is the air barrier checklist we talked about before, which you have with framing. With SIPs, it all goes away except for the very low probability of a house with a whole house fan. So virtually the entire air barrier checklist that you have in framing goes away. This is the air sealing checklist for framing we talked about earlier. All these go away except for some vents, flues, some sill plates, windows and doors, sheathing joints, which are much more widely spaced. And again, the framing to the foundation, panel to the foundation. So like 2/3 of the air sealing just goes away with SIPs. It's hard to do a SIP home that's over 1 or 1.5 ACH50. You have to really work at it. And one of the reasons I mentioned 1.5 ACH50 as a target is innovations like this almost guarantee 1 or just slightly above 1.0 ACH50. And then the thermal bridging goes away. So on the left, you have a frame house that's actually a pretty decent job, and still you see how much thermal bridging impacts on net thermal performance versus a much more effective thermal break construction system like SIPs or continuous insulation. So let's compare SIPs to continuous insulation. First, here's the baseline, a typical stick wall. And what you see is that you have the risk factor we talked about before, where you have any time air leakage can get to the cold surface. You know you have a condensation risk that can occur in cold climates. And it's prone to airflow and convection leaks because it's constructed typically with fibrous insulation and quality installation challenges when the trade force that installs insulation is paid by the piece, not by the quality of the installation. So then option A is the stick frame wall with continuous insulation. One is it's still prone to airflow and convection to that surface, but you have the buffer, the thickness of the insulation, reducing the temperature of the surface to help reduce the risk. So it minimizes the risk of condensation if we use the proper thickness. Again, the pressure on the builder would be to use thinner thicknesses than often is required to maintain the proper buffer and risk mitigation because they don't want to go 1.5 inches or greater and have to screw the rigid insulation versus nail it. And you still have a lot of quality assurance challenges putting all these layers and pieces together that are very complicated. In the case of SIPs, it's just one large panel usually that just drops in place that has a solid and homogeneous core that's air impermeable. So convection air leakage is not possible, condensation is not possible, and because of the assembly versus construction, you have many-fold greater inherent quality assurance going for you than with stick framing. So amazing just how much more innovative it is and positioned for faster, better, cheaper. So when we look at the installation on the left, which is continuous installation, you see the installation requires the drill and the screws because you have 1.5 inch furring and it's going through and going to be cantilevering all that cladding on top of it. Plus you see all the layers and sometimes there's been shrinkage from continuous rigid insulation 4x8, 4x10 sheets from one to the next, which can create an air gap. And in contrast, when you look at the SIP assembly, just dropping these large panels in place, here's a roof panel being lifted in place. It's so much less time. There's so many less trades, and you have much, much better moisture risk reduction, amazing dimensional accuracy, much greater strength, you have impact resistance, and plus greater shear strength. You have much more added volume that you can gain from the attic or from thinner walls. You have enhanced resilience with impact resilience, and with unvented attics, you don't have embers and wildfires that can get in, or in hurricanes and windstorms, wind that can get inside vents to the attic and pressurize and cause damage. You have half the wood, so you have less carbon, and all the cost savings from cycle times, inspections, waste, and rework. You know, it's just, again, I don't know that we look at these innovations for all their costs and value benefits. And take, for instance, just the thinner wall benefit. Oak Ridge National Laboratory did the calculations for a 4-inch SIP on the left versus other assemblies. And on the two on the right, the 2x6, 24 inches on center with quality installation, or a typical installation of 2x6 at 24 inches on center, in both cases, the SIP R14 outperforms the 6-inch wall. In the case of the typical installation, it outperforms it by over 20% and by a few percent for the quality installation. Again, what's all the extra cost for quality installation of grade 1 insulation and all the framing details and everything else you have to do? So just the grade 1 insulation cost savings could be $1,000 to $1,500. The air sealing and air barriers you don't have to install might be worth $1,000 to $2,000. The rework that doesn't have to be installed might be $1,000 to $1,500. The waste savings could be $1,000 to $2,000 in terms of both having to manage and move the waste into the waste dumpsters, and then having the waste dumpsters that you pay for in the tipping fees. And then you might save 5, 6, 7 days that are also worth $2,500 to $4,000. Plus, on the value side, you might be adding 30 square feet of space to a 1,400 square foot home that's worth $10,000 to $15,000 if the space is worth, let's say, $250 a square foot. Plus, the value of the extra resilience for storms, for wildfires, and for earthquakes might be worth $2,000 to $4,000. And all the extra quality and dimensional accuracy might be worth $2,000 to $4,000. And very quickly, you start to see these are huge cost factors and value factors that really affect the overall economics of what decision do you make when choosing an enclosure. And then look at attics, the most egregious interface. When you do a normal framed house with a vented attic, you don't pass the red line test. There should be a 6-sided air barrier assembly around all the installation that's fibrous insulation. And in a typical vented attic, oops, we're missing the top side air barrier. We try to compensate by making the insulation requirements thicker in the attic, but that only is a partial compromise. And then you also wind up sticking heating and cooling systems in many parts of the country up there where their performance can drop 20, 30% or more. So in contrast with a SIP attic, one, I'm saving time because it goes up so much faster. It's better because I have all that additional volume for conditioned space, for storage, whatever I choose to use it for MEP. It's more efficient, it's more comfortable, it's stronger, it's more resilient, and I save money on all the savings from not requiring insulation and air sealing and rework and risk factors. I have no cost for vents, for ridge and soffit and gable vents. I have no air barriers and air sealing details I have to pay for to anywhere near the same extent as I do in framing. And all this time savings is a significant benefit that we talked about earlier. Again, we're not looking at the full cost equation when we're comparing just by looking at a framing package bid to a SIPS bid. And when you look at the installation, you look at this vented attic on the left, and you compare it to the quality and the persistence of the performance of that SIP panel, it's an amazing difference. I put in 24 inches of insulation in my attic to cover my ducts that were running in my attic. And I went back 7, 8 years later, and the insulation dropped by more than half. It was cellulose insulation. I don't know if it was accumulating the moisture and getting weighted down or what was driving the compression, but it was amazing the lack of persistence. But when you just see fluffy stuff in the attic, you know it's more vulnerable. When workers go up there to run some cable wiring or to do some repairs, anytime anything happens virtually, you know that you're compromising the existing installation if it's not itself settling over time. And when you look at all this volume, there's so many uses, again, for conditioned space, for storage, and for any number of uses. And it even gets more dramatic how much savings increase when we actually start integrating innovation into the design process. If we know we're going to build with a SIPS house in the beginning, it can affect our overall design for huge savings. So let's say in this example, it's typical to build a framed house with a basement. What we can do, knowing that we want to use an innovation like SIPS, is instead opt for a shallow frost protected footing, get rid of the basement, the least desirable space in the home, the below grade space, and trade it off for upper level with daylight and without being up against a foundation which is cold and a basement floor that is cold and creates comfort issues that we almost always have in basements. So we trade off the less desirable basement that might be worth, let's say, $100 a square foot for an above grade space that's worth $250 a square foot. And here's how maybe the numbers accrue. We can save up to $6,000 building a shallow frost protected footing versus a whole basement. We have all the wall framing we get for free, and each end of the attic we have those walls we build that now serve a purpose. So the walls to the above grade space, the upper level. We don't have to build egress windows for maybe 1,000 to 2,000 savings. All the air sealing and air barrier details that go away that we showed you earlier might be 1,000 to 2,000 savings. All the attic venting that goes away for about 1,000 of savings. All the waste reduction and moving the waste to the dumpster go away for maybe 1,000 to 2,000 savings. And we can save 3, 4, 5, 6, 7 days of time that might be worth 1,500 to 2,500. Plus, if my 800 square feet of upper level is worth another $100, $150 a square foot to below grade space, now that's another $80,000 to $100,000 of value I've accrued. These are big numbers, and we don't normally count them. And then also just think about how much easier a business is. You get rid of the framing trade, except for maybe some interior walls. You get rid of the insulation trades. You get rid of the air sealing and air barrier trades. And you reduce the scope of work for drywall because the drywall attached to the outside walls has continuous sheathing. It no longer has to be cut, so it can be nailed on its edges to the wood studs. It can just be installed continuously wherever it wants to be against the outside wall solid sheathing. And that's less waste, it's less time. And the finishes and trim have these dimensionally dead-on true walls versus the undulations and frame walls. It's faster, it's easier, and less waste. Less for inspections and testing, for air sealing, for insulation grade 1, and for framing details that don't have to be done. Less site cleanup and waste removal. A lot of trades go away. And if the cycle time for the SIPS home is 25 days less, and cost that a builder incurs for time is $500 to $800 a day based on research done by Ibicus, that's $12,500 to $20,000 just of benefit just from the time savings that you accrue. And these numbers were calculated, $500 to $800 were calculated about 8 or 10 years ago. So again, knowing all the cost increases that have occurred in the industry, these numbers could be getting higher and higher. And again, just the velocity benefit alone for the builder, if you can build 1, 2, 3, 4 houses more a year quicker, just that starts to be in the tens and tens of thousands of dollars of benefit for increased velocity. And lastly, on the resilience side, again, SIPS just is better resistance to wildfires, to impact, to wind, to snow load, and is good or better in earthquake. So we have all these benefits. So what do we do when we have these advantages? How do we translate faster, better, cheaper? And so we have 150-year-old technology versus advanced enclosure technology. And normally what a builder will do is look at a framing bid, look at a SIPS bid, get sticker shock because of the SIP number, even though it includes all these extra cost benefits and value benefits, and can't get over the shock effect of the higher SIP price, and nothing happens. So what I've been doing is working with the industry to really calibrate what are all the cost savings benefits. I won't go through all these. We mentioned so many of the benefits for using an advanced wall system. And what are all the value benefits? You know, quality, enhanced space, and access to incentives that may occur. And what I've done is integrate those into a very detailed true cost calculator tool. It's driven by a spreadsheet. I do this with a number of my clients that have innovation they're trying to get to market, just because it really brings forward in the bidding process the huge advantages for innovation. So let me give you some case studies just to show you how it actually works. Addison Homes, owned by a good friend of mine, Todd Usher, was going to build this custom home for himself in Greenville, South Carolina. It was 2,740 square feet. I think he was pricing about $450,000. And it was normal frame walls and roof trusses, typical construction. So Todd had all of his bidding numbers and all of his costs, and we asked, could we compare it to using SIPs? But this was not a SIP optimized design. There was no place to locate posts for ridge beams to support the SIP roof, so you still had to rely on the roof trusses, so you had to expense for the roof trusses, even though using the SIPs. It wasn't on 2-foot dimensions. There are a number of factors that didn't make it a SIP optimized design. So what I did was try to show what happened to Todd in all the conditions of first getting a bid, of then comparing it to a true cost. And then later on, we looked at what would happen if we optimized this design for SIPs. So the way it works is the horizontal line is your framing cost. And anything above that line is more cost in framing for SIPs, and anything below the line is less cost or added value. So that's basically the way it worked. And when he got the bid for the SIPs and compared it to his framing bid, it was $43,000 more expensive. Again, that's the sticker shock we talked about. It was a 63% premium when you compare the SIPs bid to the framing bid, but it didn't factor in the insulation that didn't need to install, the air sealing that goes away, all the benefits of some extra volume, and everything else that accrues we talked about was not factored in. So then we compared it with true cost using the true cost tool I just showed you. And what happened is we knocked down the cost to $20,000, and we identified $7,000 of value from extra strength and resilience and quality and things that Todd valued. Again, this is all done in concert with the builder. So that reduced the premium to 10%. And Todd got real excited about SIPs because now it's down to 10%. He wanted to know if he could do more. So we sat down with the manufacturer and said, what could we do with the design to mitigate some of these cost factors and make it more SIP optimized? Remember what I said about what happens when I integrate innovation at the beginning of the design process? Everything changes. And now the cost premium dropped to $1,800 while still realizing that $7,000 extra value benefit, again, for quality, resilience, and time savings and things of that nature. So this is amazing what happens, and now Todd is going to build this house, as I understand it, with SIPs. But the decision was so much more informed once all the costs were understood and done in concert with the builder, using his or her numbers to make sure it truly aligns with their business reality. So that was the first case study. The second case study was in reverse. Here, Rob Howard with Howard Building Science, just one of the most amazing, compassionate builders you'll ever find, builds workforce housing in Granite Falls, North Carolina. So this is a 1,600 square foot home for under $200,000, and it has SIP walls and roofs. So he was already building SIP, so we wanted to better clarify for him the smart decision-making he was doing probably intuitively and get the numbers. So we got the bid numbers for framing alternatives if he built it the other way. And the reason this house was SIP optimized is, as you can see, it has a very simple roof. What he used in the floor plan was half the attic was for storage, the other half was for ceilings, for vaulted ceilings, which have more value than flat ceilings. He was on 2-foot dimensions. He used ductless mini split. It was a really nice package. So when we first compared, in this case, what the framing package that we got the bids for was to a SIP package, the SIPs was $14,000 more expensive, which would go, oh my God, what am I doing? Why am I using SIPs? It's a 56% premium. But then we did the true cost analysis, and what we realized was his net cost increase when you count all the benefits of quality, of air sealing that's integrated, of the insulation that's integrated, of all the time savings. It was only $2,000 more expensive, and he's getting $37,000 of benefits. He had a whole attic storage he wouldn't have had with a roof truss. He had vaulted ceilings he wouldn't have had with a roof truss. His walls were thinner, so he had more conditioned square footage than he would have with framing. He had, again, the quality, the resilience, all those value benefits added up to $37,000. So it's 65% more value. And we added clarification for him. This is how smart it was for you to choose to use SIPs. Last case study is Green Smith Builders. Good friend Aaron Smith, executive director of EBA, is also a builder as well. And this is a multifamily project, 2 buildings, 54 units. This is Laverne, Minnesota, right on the border of South Dakota. And it had 1 and 2 bedroom floor plans for rent. The HERS index without solar was 45. The ACH 50 without a SIP roof was 1.35 ACH 50. The SIPs were just the exterior walls, along with the walls for the hallways and the demising walls between units. It was really optimized because, again, the walls were simple to install and it was 1 hour from the plant. So again, we did the same thing. And when we had the SIP numbers, we got the framing numbers, we found out the SIP package was almost $52,000 premium, 11% greater than if he had used framing for all the exterior walls, demising walls, and hallway walls. But when he counted the true cost, the savings on the insulation, the savings on air sealing, the savings on thickness, the savings on quality, and all the benefits for resilience and so forth we talked about, the net cost savings was actually, cost was lower. It's $108,000 lower than if you built with frame walls and insulated and air sealed it separately. And the extra value, again, from the resilience and all the other quality and other benefits was $125,000. One of the big benefits, by the way, in multifamily housing is the three biggest experiences that people dislike most about multifamily housing are sharing pests, odors, and noise with adjoining units. And almost all that goes away with the SIPs demising walls. So 31% more value on this project by using SIPs, which is what Aaron knew ahead of time. He just didn't know the precise number that we were able to calculate with the tool. And so this is what I do with Housing 2.0, almost chapter by chapter for each of the experiences for optimizing community design, performance, quality, and sales. I tabulate the true costs for optimizing the user experience by, again, using all those techniques for getting rid of complexity, getting rid of waste, for mass customization, and so forth. And here in the high performance home, I took the numbers from the chapter in that book. And for doing efficient and smart, the utility cost savings are $25,000 to $60,000 over 30 years. The savings on smaller HVAC equipment and duct system layouts and so forth is $2,000 to $3,000. The maintenance savings, managing and mitigating moisture issues and so forth and using stronger assemblies is $15,000 to $30,000. The superior comfort is worth $10,000 to $20,000. Health savings is worth $30,000 to $40,000, almost as much as the energy. The way I got the health cost savings is the average household expense per year out of pocket is about $600 a year, and I assume we could reduce it 33% when you have comprehensive source control of contaminants, whole house fresh air ventilation, and hospital grade filtration, the MERV 13 filters and better. I assume you can mitigate about a third of your health cost expenses out of pocket. So that was worth about $30,000 to $40,000 over 30 years. The savings almost match the energy. The value of the sick days was $10,000 to $15,000, and on future readiness, resilience of about $10,000 to $90,000 over 10 years in insurance savings, depending on which, if you qualify for the fortified home program and the insurance savings that accrue from that certification. Water bill savings are about $8,000 to $12,000 over 30 years. The cost savings with future solar and electric upgrade savings is $15,000 to $30,000. Supply disruption power savings are worth $17,000 to $20,000. This is mostly tied to what would be the cost of a gas generator to provide equivalent supply disruption as a battery and solar system. And the solar electric system production is about $20,000 to $97,000 over its lifetime. So very conservatively adding these numbers and discounting them, I come to about $100,000 to $150,000 of benefits and value just for the homeowner, beyond all the savings for the builder that we just talked about that are not counted here. So this is all to explain that we have to look at performance differently. We focused on enclosures today, but high performance enclosures can be done faster, better, cheaper. And recognize I discounted the utility savings 50 to 60%. That I got these from the HERS reports, and HERS reports are benchmarked to the 2006 IACC, which way overstates the energy savings for new construction compared to code construction. So anyone who does that as well tries to kind of calculate these numbers on their own. You got to recognize that HERS index energy savings are fictitious for new homes. So just benchmark to a non-existent code anymore, the 2006 IECC. So here are some conclusions for today's discussion. One is that you're missing 15 to over 100% of total costs when you're trying to compare your choices of how to do high performance without a true cost comparison. Two, if your designs aren't optimized for the innovations in the design process, you're missing substantial impact on the net savings and added value. Again, another probably 100% of savings. You saw how much reduction we got when we were SIP optimized. And you also need to always use a true cost comparison to ensure your decisions are faster, better, cheaper. It just is the only way to get to the right answer. So the key finding here is that as we keep trying to take an industry that has been massively resistant to innovation and to adopt innovations, we have to be different. New innovations with significant cost savings and enhanced value just don't make it through the normal bidding process. We have to do true cost bidding. Absolutely essential to get to faster, better, cheaper. So this is the wrap up. I hope this made sense. Mike, we'll see if there are any questions or comments or whatever it may be, or discussion.
Oh, Sam, there are many, many questions we will get to. I do want to extend a couple of questions, though, to our guest, JD, because people had sent in questions for him as requested. So, JD, the first question I wanted to send over your way is in regards to smart homes. And this comes from Gregory, by the way. The Internet of Things is known to have security issues, which results in a pathway to provide hackers to possibly park onto the homeowner's router. And he's curious if Schneider has addressed this in any way and with potentially third-party confirmation.
Yeah, no, so it's a good question. Definitely a complicating question, but I'll try to have an easier answer. But a lot of our equipment that we're putting into, the residential space, especially the energy monitor, things like that, it does have its own secure cloud servers, AES 128-bit encryption, if you guys are familiar with that. We do use Amazon Web Services for some of them, so obviously their security is part of it. But another piece is actually with our wiring devices, and eventually, I think as this continues to grow, we'll see it trickle into other products too. But if you're familiar with Matter, Matter is kind of like a unifying language that is, for any smart devices out there, right? Whether you're an Apple HomeKit user, whether you're an Amazon Alexa user, right? Matter kind of is a unifying language that if a product is Matter compliant, it's going to work with any of those pieces. And the Googles, the Amazons, even Schneider Electric is part of building this Matter protocol and the security behind it. So I think there's a lot of players finally realizing that security is very important, right? So I think with this Matter protocol, which we will have in our wiring devices here in about a month or so, I think that as Matter continues to grow, more appliances or smaller products, smart home products, get added to that Matter platform. I think we'll definitely see that security, become even better.
Okay. And then we also had a question from Krina. She wanted to ask specifically on your smart panels with the apps, how obsolescence proof is it? Are these apps going to work in, say, 15 years?
Yeah, that's a great question. Obviously, we're going to continue to improve our products, as the years go on. So that is what it goes without saying, and that also applies to our app performance as well too. So the apps will continue to get updated, as with any, think of your phone, for example. As newer features come up to date in newer products, perhaps older generations of the products won't work the same way, in terms of the software, right? But that's not to say that we won't support it. So long-winded answer is as long as the features that are there today will be supported, but any future enhancements in terms of features on newer products, that may not roll into the older products that are being released today.
Hey, JD, if I could chime in, if you're in the marketplace today and you're worried about something changing technology-wise in the future, you would probably wind up not buying anything because everything's changing. And so what I know is with my car, with my computer, with almost any technology I own, it's getting constantly updated by the manufacturer or provider in real time, because it's just part of what almost any technology you buy will have automatic updates. So I expect that's kind of the same you'll see with your products.
Yeah, exactly. Thanks, Sam. Yeah, no, for sure. And also, obviously Schneider's been around for 100+ years now, so we're not going anywhere. We're a big player in the electrical space. We're not a newcomer, so there's also that longevity, that history behind us as well.
Yep, I was actually going to ask that too. As Schneider's been around for quite a while, haven't they, JD? So thanks for contributing a little bit of that history too, because I know that's a key thing. It's not just a fly-by-night company; they're very stable. So thank you, JD.
Yep,
I don't have any more questions right now for JD, but boy, Sam, you better buckle in because we got a lot of questions for you.
All right. Better not be as hard as JD's questions were.
Well, we'll see. I don't know. First, I'm going to take one of the questions from Zoran, our friend from Canada. He wanted to know, first of all, is home electric readiness justified if electricity is not green?
Yes, and that's because electric technologies are a better experience, and I think every home should be ready to keep improving the user experience, which is why the aforementioned question about will the apps keep updating? They have to, because the experiences will keep getting better. But yeah, today you may want to cook with gas, but eventually you're going to figure out that induction cooking is like half the time to boil water. It's like 10 times more precise on levels. It's like 10 times safer not to have hot surfaces around the kitchen, because as soon as I pull the cooking device, the cooking surface has no heat basically to the touch, and it is like no emissions. It's just insanely better experience. And if all it costs me to be able to switch to that induction cooking is to put a 20 amp outlet instead of a 15 amp outlet next to the at the device, because you need hardly any power for the igniter for a gas cooktop, that's a minor future-ready investment. And the same thing with heat pump water heating, and the same thing with advanced heat pumps. Just these innovations that are happening with electric technology are so much quicker than with fossil fuels. So you're just justified in just being ready to adapt to them. It's a minor cost. It's an incredibly minuscule insurance cost to be able to have a much better experience in your house as time goes on.
All right. Speaking of insurance, we had a question about insurance from Ralph. He wanted to know if you know who are some of the insurers that are offering resilience insurance savings, and how do you match the strategies, like the construction design strategies, with the savings that they offer?
What I know is when I've checked in with Institute for Business Home Safety and the Fortified Home Program, I found the range of insurance savings are about 25 to 60% with the Fortified Home certifications that are available. Again, for how roofs are installed and shear strength and continuous path loading details. So there are a number of things you do, and then essentially you qualify for these discounts. And when the insurance costs that used to be a few thousand a year now are hitting 12, 15,000 a year, those are huge savings. So let's say you're saving 3, 4, 5,000 a year on insurance costs. That is roughly $300 to $450 a month. That overwhelms anything that you're getting from your energy savings, which would typically be from a code home about $25, $30 a month for Energy Star, maybe 40 to 60 a month at best with Zero Ready. So insurance savings can be the big reason for doing the resilient construction. Even if it costs an extra $15,000, that's adding $90, $80 a month after taxes to your bill. If it's saving $300, $400 a month on insurance, that's a big number. So resilience is going to be a huge payoff, and people have to start looking at the numbers because it is way more compelling than the energy efficiency investments we're making, which themselves are good because they're positive cash flow, but they're not close to what insurance can be. But I don't know the names of the insurance companies per se. Go to the Fortified Home website, and there'll be details that probably link you to the insurance companies that provide these discounts.
And I don't have their website memorized. However, what I put in the chat box for everyone to see is the name of the organization, its acronym, and also the name of the program. So all that information, you should be able to find their site and details about their members, their programs, and all that. It's really the only insurance program out there that has to do with construction. So I definitely encourage you to look at it as well. Deborah had a question. What are some manufacturers of the thin triple pane windows?
They've changed it. The names skipped me. I knew all three when I was at IBS, and then I forgot them. I met Aaron Smith, and he told me who the new players were. It used to be Panasonic, Alpine, and I forget who the third was going to be, but it turns out three other manufacturers have stepped up. If you go and search on thin triple lowy windows, I'm sure it'll come up just from a search, but it's a good question. I forget the names.
Is one of them Alpine?
It used to be. What Aaron told me was something like 50 cents a square foot is a premium for the thin triple. So if your window, let's say is 5 by 3 is 15 square foot, that's like $8 premium for the window. That's insane for R7 window. That is so cost effective, but that's going to increase your whole wall R value 30 or 35, 40%. And it's only an extra $8 per window. Oh my goodness. That is a huge return on investment.
Speaking of insulation and walls, Zoran had a question about rigid insulation sheathing. Does it need structural backup like plywood or OSB? And if the answer to that is yes, is the plywood or OSB supposed to be against the studs?
It doesn't typically is, but it doesn't need it. A lot of the in California for years they've been doing the two-coat stucco on continuous insulation nailed right to the studs through the water control layer. So you don't need it unless you need the shear. So typically in most places, sheathing's there for shear resistance, and so you would nail directly to that. Otherwise, you got to nail it to the studs.
And then Jennifer wanted to know, where do we find these details supporting high performance goals that are being shared?
Well, Housing 2.0 is out there doing a lot. I think just the certification programs are promoting prescriptively what you want to do. I think what we do uniquely here is try to share the solutions that are getting faster, better, cheaper. We're not tethered to constraints of being in a government setting where we can't share certain preferences and observations that might be less product neutral or technology neutral or fuel neutral. Where we see a benefit, we share it. So the trouble is when you go to any kind of training that comes right from an Energy Star program or or Zero Energy Ready Home program, they will be tied to being technology and fuel neutral, product neutral. So we tend to do homework to identify solutions that work, and a lot of others do as well. We're not the only source, but do look for experts out there who are able to speak freely, but also be aware where there might be some other financial relationships that may slant the recommendations one way or the other. You have to always be cautious.
And some of the images that you were sharing on your slides, Sam, are they found in your book?
No, I'd say at least 60% are found in the book. As with almost everything I do, I don't do the same lecture twice ever. I keep updating everything and eventually just keep getting more and more new material. But the book is an amazing resource because it is the only place that puts the entire framework for how to do better homes for lower cost in a comprehensive reference document. And if a few of the images or 10% of the images are not the latest ones I use, it's just because I'm a perfectionist and I like to keep upgrading my my images quite a bit. But the book is such a powerful curation of just everything I think able to learn through decades of observing the industry. So that's that. If the images don't match up, it's still a great reference.
And to your point, Sam, about kind of being able to speak freely, I know you're a big fan of Superior Walls. Zoran wanted to let you know those precast foundations that they do have not been approved in Canada yet. So I'm sorry to break that news to you, Sam. But
and let's also mention Superior Walls not a sponsor for Housing 2.0, nor is any low E window a sponsor for Housing 2.0. Our recommendations are purely based on merit. It winds up that we love our sponsors' products a lot, which is why we go after so much to get them on board. So if we mention them, it's because we proactively reach out to those kinds of companies. But we speak a lot about products and technologies that may or may not be directly helping support our program.
Another topic that I know is near and dear to your heart, Sam, are SIPs. And both Karina and Zoran wanted to kind of know, hey, what's the deal with SIPs? How come builders aren't using them more often? How come they aren't standard construction? They've been around a long time. What's going on here?
Well, that is a great question. And the answer is, I think it's the business model the SIP industry uses is not conducive to crossing from the early adopters to mainstream builders, right? Early adopters will take on lots of additional burden. They'll take on a lot of additional requirements to figure things out themselves. And a lot of the SIP manufacturers just want to ship panels, and then you got to get a framing contractor to learn to set them, or electrician to learn to wire them. You have to learn how to get the foundation contractor to build a dead level foundation so the rest of the house is this perfectly dimensionally accurate product. So, it's not a whole product solution where you go and the SIP manufacturer comes and builds the entire enclosure for you. So because you have to learn to use the technology, that's a big, big barrier for a lot of builders. The building industry is just doesn't want to own any part of the construction process. They outsource everything to do with construction, so they have the most resources left to acquire land. So they don't build anything, they don't own any trades. And so unless the SIP industry functions as both the provider of the panels and the trade and builds the enclosure, that is a kind of disconnect with what builders will normally accept and do. So SIPs has been flatlined at like a very small percent of the net market for housing, but I think it's on a little bit of a surge in growth. I'm working hard to help the industry really find solutions to go to market. This true cost calculation system is a big first step to first clarifying and translating the value of the product. But part of it is the industry's business model itself. So I work very closely with the industry, very frank with them, is, It's okay to stay at your current market penetration and do the business the way you do. If you do desire to grow as an industry, think about these whole product solutions and as a way to really cross the chasm and get to the mainstream builders better.
Well, I kind of set you up, Sam, because we do have a series of SIPs questions for you. So we're gonna keep on this topic for a little while here. So Matt had a question. He wanted to know if you can talk a little bit about the potential problems and solutions with joints between SIP panels. And he also had another question about how is the air gap behind the cladding achieved with SIPs?
Okay, so the two-part question is the joints between panels and then the air gap between the cladding and the panel itself. So first, the joints themselves are incredibly superior to anything in frame construction. The most common detail will be two panels. The insulation has a slight groove on the inside face and the outside face, or outside skin and the inside skin, where the insulation, instead of being right up against it, there's a little bit of a groove on each panel in which you insert this spline on both sides. It's maybe a 1/2 inch by 5-inch spline that goes in. So that's what you're screwing to attach the panels. The spline just slides in. So you're getting a whole bunch of incredibly inherent airtight construction benefits. You have the thermal construction, which is absolutely perfect, grade 1 insulation with no vapor flow. Then on top of that, they first put in a very significant sealant between the butt end of the insulation that's going to be hitting the next panel insulation. So the insulation is sealed to each other. Then you have the splines, which also kind of block airflow, and often they tape the joints as well. So you have sealing and tape, you have the splines, and it's just incredibly effective. At corners, the panel will just screw through the edge of one into the end of the other panel to attach to a corner. I really recommend that people go to the SIPA.org website. There's some amazing resource materials that show all the details of SIPs and the attachments and how all the best practices for using these systems and design guidelines. You'd be amazed how much great information there is. But SIPs attach and assemble incredibly airtight. You have belts and suspenders, which lead to the 1.0, 1.1 ACH 50 numbers you see routinely on SIP homes. And then because you have the sheathing, the air gap is so much easier and low cost, right? I don't have to have it installed over a continuous insulation and hope I find the stud and figure all that out. All you do is you buy a thin foam air gap strip. Dow, DuPont sells these, I believe, and they're about 1.5 inches wide by 1/4 inch thick. It's just a foam strip, much lower cost than a wood strip, and just staple or nail it to the sheathing every 16 inches on center, 24 inches on center, and you have your air gap. And so when you first you put on over the SIP, you put the weather-resistant barrier over that, then you put on your furring strips, and you always have a sheathing that you'll hit with those, and it doesn't need to hit the studs, and then you put on the cladding on top of the furring strip. So it's a very elegant system. It's very low cost. It's much quicker. You don't have to find studs, and because it's so thin, you don't have to worry about getting to extra thicknesses where you need to use screws instead of nails.
So Brendan wants to know if have there been any long-term studies on SIP homes, and here's why he's got a bit of a concern. His concern is regards to repairability, also the ability to renovate with SIPs. He just finished a job where the SIP roof had leaked. It damaged the outer layer of the sheathing, but so much so that the structure of the SIP was compromised, and the manufacturer and the engineer both said that it was unrepairable. And so just want to know if you knew of any long-term studies or anything like that.
There are two risk factors with SIPs. One is moisture coming from the inside because you have this incredible driving force and pressure right up at the ridge where all the stack effect is accumulating at its greatest. And you have to make sure that detail where the two panels meet at the ridge is bulletproof. And normally what you do is you drape over the ridge beam something much like a house wrap material, and you seal that to the sheathing surface, and you mitigate the vapor flow potential that can happen at the ridge beam. But again, it's stunning that anyone would cheapen out on proven details for how you can keep that from happening, the vapor flow from inside through the ridge joint, and then condense on the top roof surface and virtually destroy the top sheathing in the structure. This is what happened in Juneau, Alaska, where you have the most egregious climate, and you had a famous SIP failure because of vapor got through and it went through the ridge and it just destroyed the structural outboard layer of the roof sheathing, starting from the ridge and dripping down the roof line. So that's from moisture coming from the inside. There's no excuse for moisture getting in from the outside. The flashing details we have today are just tried, proven details. I've ripped my roof off twice on a house I'm living in. Twice. The first time was, I think the roof hadn't been replaced in 30 years. The second time was maybe 20 years hail damage that damaged the roof. I've never had a speck of moisture on the roof sheathing on my homes. It's a simple roof, shed roof. It's easy to detail, easy to manage water. If you're going to create these incredibly complex roof designs, you're violating the function of the roof itself, which is again to shed weather. And if you're going to create conditions where leakage can happen, that's on you. I wouldn't want that with SIPs or frame construction. It's going to be expensive either way. But we know how to build roofs that will just have no moisture damage. And I don't know why what happened. You had to do something so flagrantly unprofessional to create a condition where moisture can happen. We know how to flash. We know how to do the roof protection with the underlayment and with the roofing itself and the flashing details and drip edge flashing and capillary breaks. This is routine. So there should be zero risk of moisture getting in through the roof from the outside. And again, the inside, you have to know the details to do at the ridge just to protect the stack effect pressure up against it. So if you're encountering a problem, I will say that's a stunning error and omission by either the architect or the builder who built the home. It's not the reason not to use technology. It's the reason to be diligent about doing it correctly.
I want to stick with SIP just a little bit more because Deborah had a question about them. Are there still cost savings with one-story homes where the insulation would be high up at the roof, or is there like a maximum footprint size for cost effectiveness? Because she's thinking of it as, it seems like if you have a larger one-story footprint, there might be additional costs unless they're small footprints. But she is a fan. I mean, she thinks that 1.5 story homes would be ideal for SIPs. But talk a little bit about the cost savings with one-story homes.
Cost savings are agnostic or indifferent to 1-story, 2-story, or size. The biggest factors that contribute to cost effectiveness for SIPs will be, again, simple roofs versus complex roofs. 2-foot dimensions are great, but not critical. If you have plumbing on outside walls, you're going to want to fur out your plumbing and not put the plumbing in the SIP wall. So you want plumbing on interior walls as much as possible. You want to, there are some excessive window opening sizes where even in a jumbo panel, you might not be able to get a certain window size without some additional structure. There's some basic guidelines that we'll be putting together, and I'll tell people to go at the SIP website and check those out. But this is like are, like I said, indifferent to size. The costs work either way. The question is simply accounting. You're displacing, you're adding costs for an advanced assembly versus framing, but you're saving costs on insulation, you're saving costs on air sealing, you're saving costs on quality control, you're saving costs on finishes, you're saving costs on time. And when you put all that together and run the calculus and look at the numbers, then you get your answer. But I did find that the number of savings numbers did seem to be bigger on multifamily versus single family. That was something I will say stood out for me when I ran some case studies. But the big thing is you don't want to have your design so disconnected from the SIP panel logistics that you still need tons of posts and columns and all these things happening in the walls because you didn't design it for the SIPs. So that's the biggest takeaway I say about cost. Just optimize for SIPs.
All right, we're going to move away from SIPs now.
Good.
We got a question from Gregory about Passive House. His comment was that it's got a built-in verification which can address many of the reliability and trust issues that you were mentioning earlier. But he does have a disagreement with you on one thing. One of your slides talked about changing the air sealing value of Passive House from 0.6 to 1.5. He disagrees with that. Any response to that?
That's not what I said. I said, if I'm a builder, if I'm in the building industry, instead of having a spaghetti of different ACH 50 targets, I would do 1.5 ACH 50. I think that's where the industry can get to with a modicum of discipline. They can't get to 0.6 with a modicum of discipline. That's a wholesale transformation and huge infrastructure in terms of installation capabilities and so forth. 1.5 we can do. That's the number I believe. More importantly, I can get to 1.5, I get to zero energy, I can get to huge comfort, I can get to huge quiet benefits, I can get to no utility bills, I can get to amazing health benefits. So the benefit to going to 0.6 and the more aggressive thermal control levels in Passive House is mostly limited from my lens to the additional resilience because the house can float longer. And if that's worth all the extra cost to you, great, then do it. Passive House stands as the epitome of what you could do in terms of the most rigorous certification program for energy efficient performance. That's the most rigorous. I personally don't go that far. I don't need as much insulation under the slab. I don't think I need as much wall insulation. I would make my investments elsewhere, but that's the way I crunch the numbers. What I get to, I'm seeing zero energy ready homes far below the Passive House requirements, have no energy bill, even though they use all the electricity for both the house and the car. And the house is amazing when I've been inside the home and how it lives. And so I'm going, that's good enough for me. But pick your own level. There's no right answer. If you want to do Passive House, that's great. If you make the numbers work. I'm trying to work with mainstream builders. That's always been my target. I want to get mainstream builders to build great houses. I'd be real excited if we all did 1.5 ACH 50 and less. Passive House, there's always room for something to be the penultimate highest level, and that I think Passive House kind of just enjoy being that for energy efficient performance.
And Ralph asked actually about the ACH 50 number that you had. He wanted to know how you came up with it. Is it an estimate, or is it from an energy model based on component options, or something else entirely?
Generally, it's from, I've had the ability, well, I had the privilege running 2 national programs to virtually travel 46 different states, see thousands and thousands of home builders, worth of projects, tens of thousands of homes worth of construction, actually under and after completion of construction, and and observe actual utility bills and performance and how homes live at various different levels. And I come away, when I look at numbers and I look at everything I've seen, 1.5 seems to work. You know, you can knock yourself out and put in tens of thousands of hours trying to get to a perfect number, but 1.5 just with whatever wisdom I've acquired and understanding, that seems to be the number that works for me as the mainstream builder target that I would advocate today. And for no other reason, again, these advanced wall systems get you there automatically. And I think we undervalue air sealing because we only look at it from the energy loss side of the equation when we come up with those targets for the various climate zones. But in every climate zone, you want to keep all those contaminants outside, and you want also the extra resilience. So just let's all go to 1.5.
All right, Sam, final question is for Zoran. He wanted to know, are batteries common only with solar systems, or can they be used for either peak shaving or load shedding?
Yes, they can be used for peak shaving and load shedding. The economics vary by each application. And it depends, you know, if you're in a time of use utility rate situation for residential, and you know you're looking at 20+ cents a kilowatt hour for peak, and you're looking at 3 cents an hour, 4 cents an hour for off peak. If I can charge off peak at 3 cents a kilowatt hour and sell back to the grid at at retail rate at 20 cents an hour, sometimes those economics just justify batteries by themselves, and the utility comes out a winner because it mitigates the need to build that extra peak power plant that's very expensive to run. That's a huge benefit for them. However, the best way of looking at the economics for me is I see more and more people like installing natural gas generators, which during power failure kick in and provide power during supply disruption. And they emit a lot of emissions, sometimes so much so that they've really endangered people living in the house, as emissions seep into the house with the generator in close proximity. And the cost is pretty high. A natural gas generator will be anywhere from $13,000 to $18,000. You have to tune it up once a year, a few $100s. You got to run it every month for X number of hours just to keep it operational. There's a lot going on with a gas generator. If I have just a battery, I mitigate all that, and it can be charged by a complementary solar system, I may have just a really cost-effective way to go that's far better than the cost of that natural gas generator. Remember, I keep saying the electric technologies user experience will keep, I think, surpassing the fossil fuel options that are out there. So I think the choices will go in that direction.
All right, Sam. Checking to see if we have any final questions. We've hit them. There's certainly comments that have been shared, but thank you as well. So I certainly want to thank our audience for asking all these wonderful questions. And there was one that came in that I'll get to JD over at Schneider Electric. So thank you, certainly, everyone, for sending your questions. We really do appreciate you attending. And this is the end of our third seminar, but that means we're only halfway through. We still got 3 more to go. In fact, our next seminar is going to take place 2 weeks from today. That's Thursday, March 21st, at the usual start time of 2 p.m. Eastern. We're going to be discussing 5 low to no cost best practices to help you get to zero. So thank you so much for attending today. Thank you once again to Schneider Electric and certainly JD Gill for joining us, the Jinko Solar, Mitsubishi Electric, and Panasonic Healthy Indoor Living Solutions for their generous sponsorships of this program. Until next time, don't forget to change your clocks this weekend. It's time to spring forward an hour. So stay safe, stay healthy, and take care, everyone. So long.